Hello students, welcome back. Let's go to section 5 of this notebook. Eigenvectors and eigenvalues. Eigenvectors. Have you heard about this term? Maybe not. Eigenvalues. Have you? I hope the answer is yes, because I've been using this term way back from, possibly from chapter 2, at least from chapter 3 I've been using this term. In case there are some students who are a little bit hazy about these, let's have a motivating example which will double as a reminder. A motivating example from chapter 4, and here's a homogeneous linear ODE with constant coefficients, like this. It's third order. Now, how do you solve it? Well, we can use a Laplace transform method, but for this example, it's going to be a little bit more convenient if you use the substitution method. So let's begin with an educated guess, y equals to e to the st power. And then we simply take the derivatives and plug those in. So here we go. We take the derivatives just by chain rule. So it's an easy computation. Is everybody following? Okay, all right. Let's plug all those in back into the original equation. This one goes in place of the third derivative. This one goes in place of the second derivative, and so on. If you do, this is what you're going to get. Now what? Does everybody recall? Here, we can divide by this e to the st power because it's never zero. Exponential is never zero, so you can always divide by that. Then you're going to get all those exponentials off, and you're going to get a polynomial equation, which we call the characteristic equation. From here, divide by exponential, and this is what you're going to get, highlighted in blue. Does it make sense, everybody? All right, we have this characteristic equation. By the way, this part, blue part, is called characteristic polynomial. Now set the characteristic polynomial equal to 0 and find out its roots, its zeros, and here's the factorization, and here are the zeros. S equals to 0, or S equals to -4, or S equals to 2, and these are called the eigenvalues. So the zeros of the characteristic polynomial. Now, how do we use these eigenvalues? Again, another reminder. Let's go back to the original educated guess, e to the st power, where s is 0, -4, and 2 respectively. And we get these three solutions of the original equation, and these three happens to be linearly independent. And yes, it is possible to prove that any eigenvectors associated with, oh, excuse me, I should not be using that kind of term. Sorry about that. Forget about the general theorem in linear algebra. Where was I? Characteristic equation, and then eigenvalues, and then from each eigenvalue we got the solutions. All right, these solutions are called eigenfunctions or eigenvectors. These are functions, so naturally they can be called eigenfunctions, and they are associated to eigenvalues, so that's where eigen is coming into play. But why eigenvectors? That's because the set of all infinitely differentiable real functions form a vector space. So each function there can be called a vectors, so they are associated to the term eigenvectors. Some people call them eigenfunctions, but more commonly known as eigenvectors rather. So from these three eigenvectors, we get the general solution, and we get it by simply taking the linear combination of those, c1y1 plus c2y2 plus c3y3. So that was something we had been doing in chapter 3 and chapter 4, and here is a summary of the terms. This polynomial, this one, is called the characteristic polynomial. And the zeros of the characteristic polynomial are called the eigenvalues. And the solutions associated to each of these eigenvalues is called eigenvectors. And that's how these terms, eigenvectors, eigenvalues, and The characteristic polynomial did not show up in this title, but characteristic polynomial as well. That's how all these are related in terms of linear differential equations. And that's something we have been doing in chapters 3 and 4. Now keep that in your mind somewhere. And now we're going to take an alternative viewpoint. We're going to study the same concept, or rather similar concept, in the viewpoint of matrices. The natural question here is, of course, are they related? And the natural answer, of course, is yes, they are related. Duh. Why else are we going to be using the same terms? Yes, they are related. Exactly how they are related is going to be the answer for modules 14 and 15, and it's a big deal as a matter of fact. If I give you a brief preview of what's to come, basically what we do is to form a system of linear ODEs. So it's even more general than just one linear ODE, make a system, and then get a matrix expression of that, and associate eigenvalues and eigenvectors and characteristic polynomials of that matrix. And then that's how they are related. So here, let's forget about those differential equations for the time being, and let's focus upon matrices only. All right, ready? Here we go. Let V be a vector space, then a linear map from V to itself is called a linear operator. So if V is Rn, n tuple of real numbers, then this linear operator will correspond to an n by n matrix, n by n real matrix. If it is Cn, n tuple of complex numbers, then n by n complex matrices. Now, if V is a function space, infinitely differentiable real functions, in that case, matrix expression is going to be, that's going to be a bit of a challenge. Still, we can consider them as linear operators, and let's consider eigenvectors and eigenvalues of those linear operator, and here we go. A non-zero vector V is called an eigenvector if it satisfies this kind of equation. L of V equal to lambda times V. If it is zero vector, then this is trivial because L of V is 0, and lambda times zero vector is also 0, so 0 equals to 0, that's trivial. If it is non-zero vector, it's not that trivial. So if that kind of relation exists, then that non-zero vector V is called an eigenvector, and this scalar lambda is called an eigenvalue. Now V, the eigenvector, is a non-zero vector, but lambda, the scalar, can be 0, can sometimes be 0. So don't be confused about here, be careful here. It's rather common mistakes many people make. Okay, we went through the definitions, so let's go to an example. Here's a simplest example. If you have a diagonal matrix, then the principal diagonal entries are eigenvalues. You can easily check those out. Get standard basis factor E1, E2, E3, and so on. This is E1, 1 and all 0, 0, 0, everything. And take this matrix multiplication. First row times the column, and then we have lambda, and then all 0, 0, 0. So what do you get? Lambda 1 times that. All the other rows will just give you 0. You can easily check those out. So yes, E1 is an eigenvector, and eigenvalue is lambda 1. Likewise, if you do E2, then only this one will contribute. Everything else will be killed by all those zeros. So we have lambda 2 times E2. So E2 is also an eigenvector, and associated eigenvalue is lambda 2, and so on and so forth. Here, lambdas can take 0 values. So eigenvalue may be 0, but eigenvectors, they are never 0 because there is 1 somewhere. Okay, that was an example for a diagonal matrix, and here's another simple example. Let V be the space of all infinitely differentiable real functions, and let D be the derivative operator. And what is the eigenvector associated to eigenvalue lambda? And here's the answer, e to the lambda t power. By the way, that's why we made that educated guess early on in that motivating example with the exponential function. That's why. So if you take the derivative, we get that. By the way, this is not the only eigenvector. If you multiply any constant k, this will be still okay. K times that, and then k times that. So this is the original, so lambda times the vector. So yes, everything is good. So if you have any eigenvector, then by multiplying by k, we can get another eigenvector. Oh, excuse me, multiply a non-zero k. If k equals to 0, then you're going to get 0 vector, and that's moot. So multiplying by any non-zero constant k, we can get another eigenvector, which means if you have one eigenvector, then consequently there are infinitely many. But then again, if you have to find just one eigenvector, then why would you bother setting some arbitrary k? Let's keep it simple. Keep it as k equals to 1. Okay, here is the hardest type of example problem here. We have a 3 by 3 matrix, okay. And then let's go to the first problem. Show that 1, negative 1, 1 is an eigenvector, and also find the associated eigenvalue. So a times v is lambda times v. So basically it's this. A times v is lambda times v. We have to find it out. And v is of course 1, negative 1, 1. How do we do that? It's simple. Just calculate a times v. Here, a times v. Just do the matrix multiplication, and here we go. Detailed computation is left to the student. If you do it right, you're going to get 2, negative 2, comma 2. And you can easily see that is 2 times v. So whenever you have an eigenvector, or a candidate of an eigenvector, it's easy to find an eigenvalue. Just do the matrix multiplication and then compare with the original. Now, what about the other way around? Show that lambda 2 is an eigenvalue, also find an associated eigenvector. Well, the answer should be this, but pretend you don't see it. Let's find it out. Yeah, previously, lambda was unknown, but we found that lambda is equal to 2. Here, lambda is equal to 2. V is unknowns, so the answer should be this one. But pretend you don't see that, and let's try to find out. How do we do that? This is going to be a bit harder. Basically, you have to do this. A times v is 2v, because you see previously v was known and this value was unknown, but this time it's the other way around. Lambda is given as 2, and v is unknown, and v is a vector, so basically it's this, x, y, z. Now previously we had only one unknown value, lambda value, but here we have 3 unknown values, x, y, z, so this is going to be a bit harder. It's going to be a system of linear equations, and okay, let's solve it. System of linear equations, so let's take the matrix multiplication of this part, left-hand side. If you do it right, you're going to get this computation. And comparing each line, you're going to get a system of 3 equations and 3 unknowns. 3 equations and 3 unknowns looks like it's well set. But if it is a well-posed problem and if it has a unique solution, that's no good, because unique solution means it's just a trivial solution. X, y, z equal to 0, 0, 0. That's not what we are looking for, because eigenvector should not be a 0 vector. So we are looking for a situation that we have infinitely many solutions. Remember, if you have a system of linear equations, either unique solution, no solution, or infinitely many solutions. We are looking for the case where we have infinitely many solutions. So how do you do that? Well, this is the way I handled. Simplest part is the second equation, so from here, solve for y, and then plug in y equal to negative z to the first equation, blue, and then I got x equal to z. I hope I can do this really quickly because this is tedious but elementary computation. And then let's check. Y is negative z and x equals to z, and plug those into the third equation, green. And let's see if it works, and it works. 2z equal to 2z, which means true. So yes, it works out. So y is negative z and x is z. So we have x comma y comma z is z comma negative z comma z. Remember, x blue is given by z, and that's from the second step. And y equals to negative z is coming from here, red. So anything of this form, z comma negative z comma z, is going to be an eigenvector. Remember, there are infinitely many. But then again, we have to just find one, so let's keep it simple. Plug in z equals to 1, then we get an eigenvector, 1 comma negative 1 comma 1. Yes, you can plug in z equals to something else, like 3, then you get 3, negative 3, 3. Plug in square root of 5, you get square root of 5, negative square root of 5, comma square root of 5, and so on and so forth. But why would anybody bother with such complicated numbers? Z equals to 1 is the best in this case. But no 0. Don't plug in 0. If you plug in 0, you get 0, 0, 0. 0 vector is not an eigenvector. You get nowhere. Sometimes if you have denominator, then you put in common denominator, LCD, so that you can kill off all those denominators. But otherwise, usually 1 is the best choice. Alright, that's how you work out eigenvectors and eigenvalues. And let's have a recap here. If you know eigenvector and finding out associated eigenvalue, that's really easy. Just one-line computation. Well, okay, matrix computation may be a bit complicated, but with computer it's easy. If you know eigenvalue, finding eigenvector is a bit harder because you have to solve a system of linear equations. But again, this is just elementary question. Now, in real-life situation, you'll have to do this way. You have to find out an eigenvalue in a certain way, and based upon that eigenvalue, you'll have to find out eigenvectors. So how do you do that? You can find eigenvalues through characteristic equation, which is obtained like the determinant of A minus Ti equal to 0, where I is the identity matrix. Or equivalently, Ti minus A. It's the same because 0 is equal to negative 0, so whether putting negative doesn't change anything here. So this way or that way is the same thing. I copied this from my linear algebra notebook, and our textbook for linear algebra is using this convention, but our current textbook is actually taking this convention. But I hope nobody will be confused here because 0 equals to negative 0. Don't ask me why, and that's a significant question. Let's just use it. So let's go to the previous example and find out the eigenvalues, the same matrix here, and determine all the eigenvalues. How do I do that? Basically, we have to calculate A minus Ti. So A is the original matrix here, and Ti is T times I, so T, like this. You see? 1 times t is t, so 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, we can do like this. And then do the subtraction, you get this matrix. And then take the determinant, oh boy. If you use all those crisscross, then you're going to get something like this, and this is a cubic equation of t. Here I use all this rigorous paper and pencil algebraic method, but you don't have to. You can use computer algebra system once you get here, and you're going to get solutions. So once you have those solutions, those are eigenvectors, those are eigenvalues, so you can use a previous method to find out the eigenvectors. Tedious process, but each process or each step is elementary. Okay, so much for eigenvectors. And in the next video, we're going to talk about a little bit more theory about eigenvectors and eigenvalues